It's a real pleasure to be here in front of you all and to represent CERN at this event. So what I'm going to do is I'm going to start off actually with a little video of my own, prepared for us by our collaborators from HP. So that, by way of introduction, now what I will do is to talk about a number of the things that you saw in that video in a little bit more detail. In 20 minutes, it's a bit difficult to describe everything that I would like to say. I've worked at CERN. I'm a relative newcomer. I've worked there only 26 years, and I'm starting to understand now some of the fundamental objectives of the organization and some of the big science that's behind all of this. So just some acknowledgements that many people have contributed to this presentation with information that's in the public domain. And let me start with this. So this is really what it's all about. I need to put into some context as to what CERN does, why it has the equipment it has, and what its needs are in terms of technology. So here we have a nice inflationary model of the universe, starting with the Big Bang here to where we are today. Now, to give you some idea of the scale here, if last night, when we were having our drinks, we decided to create the universe, and then every hour represents 1 billion years, we are just before 9 o'clock today, creating mankind. So in a sort of blink of an eye, mankind has been created right here. So the universe has existed for a very long time, and during that time it has gone from being very, very hot to being really quite cold, now down to 3 degrees Kelvin. And one of the things that happens when you go from a very, very hot system to a very, very cold system is all sorts of things sort of crystallize out of it. So we've got planets, we've got galaxies, we've got all sorts of stuff. But these really don't represent the fundamental elements of the universe as a whole. Those existed only way, way back here. And what happens as it cooled, all of these structures, all the symmetry that exists here is broken, and all of these things crystallize out into very specific structures. So what we try to do is to understand what the symmetry, what the fundamental particles, what the origin of the forces and the matter, what it was right at the very beginning. And so in order to do that, we have to create that, those conditions, albeit for a very short period of time, to understand in terms of the fundamental particles what existed, what we all created from, and how do all the forces of nature actually interact, and how are they brought into existence. And so we have a standard model. And the standard model of particle physics is actually very, very simple. It talks about matter particles, it talks about force particles, but it doesn't explain everything. And that's really where there is one fundamental question that is remaining, is why not? What is wrong with this model that we've built up over the last 30 years? Now, part of the problem is that we build machines to actually look at what the theory predicts, to find the particles that are predicted, but the machines can only create events, create particles down to a certain level of resolution, granularity. The bigger the machine, the greater the level of resolution, the deeper you can probe into the matter of the universe. And this model has been very successful for the machines we've had up to now, up to the energy levels we've had now. The LHC is a transition point. The new accelerator is a transition point because this theory doesn't explain what happens beyond a certain energy level, beyond 1 tera electron volt. And the new LHC machine will go beyond that. So we're not quite sure what we're going to see. But what we do see will drive theory from that point on. So it will indicate which of the many theories now exist for how the standard model should evolve will be the correct one, and which is the theory that should be then followed. In addition, there are some very big fundamental questions. Where do particles get their mass from? Why are things heavy? Why do they have the weight that they do? Where has all the antimatter gotten? In a universe that started off supposedly with equal amounts of matter and antimatter, why now do we see matter but not antimatter? We also know from cosmology that a lot of gravitational effects can be seen but not explained by the actual amount of matter in the universe. So there's some mass there that we don't see. What is dark matter made of? What else is out there in terms of things like dark energy? We know that the universe is expanding. It's in a state of almost equilibrium with gravitation and expansion sort of equaling each other out. So it's expanding very, very slowly, just at the right rate. So there's a dark energy